let's say dog bites men, right? And another sentence I write men bites dog, correct? Both of sentences have kind of similar words like dog, and then men and bites and bites. So it becomes really important to understand the position of these words, like how the position 1 2 3 are set, so that the values can map properly. So even if we do embedding, so let's say we do 512 embeddings, right, of dog, correct? And then we generate all these numbers, like let's say D12, D1512. For all these numbers, when it comes in this sentence, then these embeddings will be different. And when we come to the second sentence, when man bites dog, then these dog embeddings will be different. So there will be another context will be added, so that the LLM can understand the different meaning of different sentences. Like there are different meaning happening. Here man is biting the dog. Here dog is biting the man. So that's what happens in embeddings and positioning. And then self-attention, when we try to understand each and every words, and feed forward will happen with multiple layers. And then logic gets applied, and then we generate the next token. And this is how the transformer architecture works. Correct? I just try to make it very straightforward and simple for you so that you can understand easily, right? Because we have lots of things to cover. We have all these things to cover in coming days, like prompt engineering we'll cover building with LLM APIs, embeddings, RAG, agents, tool. And if I say even RAG, right, it's not a simple RAG. It's like why RAG exists to the production RAG we'll go. We'll also discuss about graph RAG, you know, we'll discuss about agentic RAG, corrective RAG, adaptive RAG. We'll talk about hallucinations about RAG. Means with this content and my personal expertise, so there are around 215 topics that we're gonna discuss in this complete video series if you keep on following up, right? So you see that attention paper, this paper we talk about, right? This is changed everything, and this was published by Google in 2017. Sam Altman got leverage of all this paper and built ChatGPT. It's like, so if you try to understand transformers, right? It's like having a very minute kind of matrix, or you could say statistical calculation of weight and parameters, right? And parameters, which once any input comes in terms of vector embeddings, right? That is how, or you can say don't call it vector embedding because I haven't told you vector embedding. So just call it a list of numbers comes in terms of matrix, and it gives us a list of numbers in terms of matrix. That's what this transformer does, and this transformer is out of trained on lots of data, and on basis of those data we run this complete LLMs. So you see, so scale and instruction tuning before 2022, people I did myself to do classical ML AI, right? Data drift, like fraud detection, correct? And you could say there was outliner detection, right? There was all data problem that we were trying to solve, like trying to figure out the positives and the negatives inside these, the complete data set that is coming. We were trying to build a Kubernetes cluster there. We're trying to deploy machine learning models, and these machine learning models are working together to figure out a solution. But that exactly what changed in 2022, that this LLM got into like picture, and that LLM is like a centralized LLM that is empowering all over the globe, and that is powered by transformer. Okay, and this transformer, it got trained on millions and millions of data, all over the globe. It's from the internet, it's from GitHub, it's from books, disguised books, everything possible humanity has on internet and digital side. That transformer got trained, and now we have this LLM. We have this complete LLM where we communicate and we get the data. That what changed So if you talk about the scale and instruction tuning, made models generally useful, not just clever. Chat interface. Basically, the best idea was chat interface, giving the chat interface to the user so that they can directly communicate with the LLM and get an answer. It's like this LLM, this transformer was trained to take data and give output. So that's the initial phase. You try to communicate with it, try to write poems initially, try to write a joke that you like. Kind of this is how it's initially started. So that is that is how it started in 2022. Now, but the way it's going right now, it's pretty crazy. Now let's try to understand what are tokens. So once you try to understand tokens, then every time think a word, right, as a language atoms, right? Language atoms. This means that, let's say, we know that in an atom, that is the smallest particle possible in a molecule. Means there are other smallest particle, like there is neutron, there is electron, etc. But atom is that we call word, that language atom. That language atom is kind of tokens, and that is decided on the base of a algorithm BPE. BPE is basically byte pair encoding, right? That you need to understand. Byte pair encoding. What happens is, if I tell you a sentence, I love AI agents, right? Videos by NIT Monk. Okay, if I'll tell you this sentence, right, and let's say I'll try to take this word, right, and this is I, right, single word, single character. Then I'll try to search in this complete sentence, and I'll find that I is a standalone I sitting somewhere. I is also sitting with AI. I is also sitting with video. Then I'll try to figure out if I can make I as a standalone word or not. Like similar way, I'll try to go with love, right? Love, I'll select L and try to search the complete sentence, for example, and see what are the possibility if L could be a single word. And then if I'm not happy with L, then I try to do LO. Then I'll try to do LOV. Then I try to do LOVE. At the place of LOV, I see, yeah, LOV could be a kind of a word and language atoms. So that language atoms is tokens. This is tokens. So if I try to see, that is the, like, model do not see letters or word, they see a token ID. So once we understand these tokens, right, then we try to store these tokens somewhere. We try to store it, let's say, in a set of array, and that array is kind of positioned with indexes, and that indexes is like token ID. So once you understand these tokens, right, as language atoms, right, and that is finalized by BPE, byte pair encoding, correct, encoding, then you will have idea that, if let's say, if I'll say this sentence, that LLMs process text using tokens, not whole words, right? Here you see it has taken full stop as a token, a comma as a token. You see over here it has taken whole as a token, right? You see tokens it has taken as a token, also with a space. That's exactly what the tokens are. Means tokens are not just a word designed with characters. It's also with punctuation. It's also with spaces. And that's where how you define this token. So if you try to see, right, I have added these two papers. There is a tokenizer. I will open the tokenizer and try to see, correct, from here, right? So I said I love NIT, I love AI agents, uh, videos by, let me make it a little bigger, by NIT Monk. So see how it's trying to make, and right now it's like it's trying to say that this NIT is a different token, because NIT is coming from my college where I graduated. It's one of the India's topmost college, top 10 college it is, right, in India, right? And monk is kind of a noun, to represent a monk, right? So that is NIT monk, and saying taking it as two different, word. Even it's trying to differentiate mon and k. We'll try to understand how it actually is try to take these words, because that's it has taken all the vocabularies of the complete languages. It has taken for English, it has taken for let's say Hindi, it has taken for Chinese, and every place. That's the whole game, and that's where these tokens are getting generated on the BPE method, trying to figure out byte pair encoding. So these are these are different set of tokens, their characters. So the rule of thumb is 4 character is kind of one token. So there is a 4 character is one token, you can see, and this 100 tokens around 25 words. So that is the rule of thumb. If 4 characters are there, and then we'll say this will contain one token. So for now, once you see that ChatGPT or OpenAI or let's say Claude takes, for example, 100,000 tokens as an input. So they are not characters, they are not words, they are kind of combination of those. Let's say if you rule of thumb we say that 4 character becomes one word, then if they are taking 100,000 tokens, then around 4 lakh words they are taking, or 4 lakh characters they are taking as an input. So that's a rule of thumb. And also this is the BPA formula. This is how they try to build it. Try to figure out which set of characters putting together can be a word, and that can be used, that could have a meaning. That is token. Having this number representing these tokens is a token ID. So now you got the point of tokens and token ID. Correct. So always try to think in terms of tokens. Once you try to think in terms of token, then you will have ability to think in terms of token usage, right? Because that is a major bigger problem that AI agent engineers trying to solve. Once you try to understand in token usage, then you will be started talking in terms of AI agent, system prompt, visual prompt, or let's say skills that you're gonna get, or the tools that you're gonna connect, correct? Or let's say the MCP that you're gonna communicate, or let's say you knowledge base that you're gonna add, or let's say the retrieval mechanism that you're gonna apply. All this becomes really important, because everywhere it's all about token usage, because this is the only thing these LLM understand. Because LLMs are just, they are just a probabilistic reasoning model, probabilistic reasoning model. They take a data and they take an input and they produce an output. That's what exactly happening, and that's exactly what LLM does. And that's where we are trying to input, let's say, natural language in any language. Like let's say we're trying to put it in Hindi, and try to do it in Chinese, in Russian, in French, yeah, in English, and all these getting converted into tokens, and then token IDs are there to represent them, right, everywhere. So this is the most important part you need to understand. So they start from a character and merge the most frequent character in the subwords. That is byte pair encoding. Common words become one token, rare words split into pieces. That is what I am trying to tell you over here. Now let's look at tokenization. Once you understand the tokens, then let's understand about tokenization. The process of, this is the process of splitting text into tokens, correct, and mapping each token is integer ID done by algorithm BPA. Just we saw. You see, I have added all these links. Neutral, empty of rare word of subword. This is published paper. I have added a Wikipedia link over here. I have added an OpenAI tokenizer so that you can actually write the sentence and see how the tokenization is working, isn't it? And then I already explained to you about BPE. This is the thing that you have to think about. BPE is, it's like byte pair encoding. Because of without it, you won't be able to imagine how these tokens will be shared or saved or put somewhere. And And without this token ID, how you gonna map all these different set of tokens any place, right? So there is common words is equal to one token, rare long words is equal to many tokens. This is what it's happening. Common word is equal to one token, rare or long word is many tokens. That's what we said, rule of thumb, where we talked about 4 character becomes one token, right? That you always try to remember, and that one token ID becomes token ID. We'll see how this token and token ID are sitting together, correct? So see here, again we'll try to see the BPE. There is a lower, then it takes LO, then LOW, and then LOWE, and LOWE, and then LOWER. So it says that lower has the more probability of being as a word, and then it selects as a token. Even if you try to say like this, there is a word open AI, correct? Then OpenAI will be treated as a two token, because open appears most of the time, as per the byte pair encoding. It goes in the list of vocabulary that it has, and the AI terms comes most of the time in the complete vocabulary. So open will be a different token, AI will be a different token. So you can think about all those possibilities of different combination of words. Like, let's say I'll say nationalization, right? Nationalization is kind of NATIONL, nationalization, right? So here what happens, it cuts into 3 pieces. So that's byte pair encoding, and it's nation and ul and igation, right? That's how these tokens are working. So why it's really important, because if you think that LLM can store direct, or communicate with direct English words, correct, English words, then it will become very very difficult and very big vocabulary. Like, for example, if you say run, right, then what are different set of combination you can do with run? So I can do running, right? I can do runner, right? I can do runs, right? I can do other set of, for example, different combination of word with runner, right? Okay, and I can do also ran, but the past tense, right? So all these, so for each and every single word, we'll have different set of combination, and that becomes difficult to store. So that is where we have to get that language item, correct? And that language item is really critical for the complete ecosystem of LLMs. And that once that language item comes in, we start calling it token. And once we start calling it token, right, once we start calling it token, then there is a token ID for each and every token, correct? This is how things keep on going, and this is how BP works. Right. So I hope till now you got all the points about tokens, token IDs, LLMs, language items. Now let's talk about vectors and embeddings, right? Embeddings versus tokens. So first try to understand this. This is really important. If you understood this, right, then no, you will never, first of all, never like be confused about embeddings at all. So think about, let's say there are 4 basically animals. There is cat, there is dog, there is tiger, correct, and there is this lion, right? So you know already that in computer science or in computer there are ALUs, arithmetic logical units, or I'm going to just assembly language or the chip level, where everything is understood by 0 and 1, isn't it? That 0 and 1. So if you see this cat and dog and tiger and lion, these units will not understand. So let's say I'll try to do it with 1 as cat, or 2 as dog, and 3 as animal, 4 as lion. And once this 1 is there, then maybe it will turn to binary, and someone will be able to represent this as, let's say, 0 1 or something like that. 2 will be there, and there will be 1 1, for example, a 1 0, for example. This way we will be able to implement it, like 1 1 for 3, for example. Like, I guess if I remember 1 1 for 3, then 1 1. So this will become 2 to the power 0, this will become 2 to the power 1, and this is 1 is 2, yes. So 3. 3 is 1 1, correct. So it will represent as 1 1, and this is 4. Now if I'll ask the computer which comes closer, which is kind of similar. So it definitely gonna say one is closer to two, then cat is similar to dog. But that is very ambiguous. You don't have any kind of facts or features, figures to make sure that one is equal to two. You have to do some kind of feature extraction, like have to represent it properly. So let's do the feature extraction. So we will try to build a table. We'll try to put an animal over here. Let me make this board a little bigger so that we understand properly. Correct. And let me delete it once and let me try again. So first there was cat, there was dog, there was tiger, and there was lion, isn't it? This is one, this is two, this is three, this is four. Now I said that let's make feature so that we totally get understanding. Like if I say a1 equal to 2 or 1 is closer to 2, basically not equal to 2, but I'll say closer to 2. 1 is closer to 2. So then cat and dog is closer to 2. Sorry, cat and dog is closer, but that is very very ambiguous. That is very ambiguous. It's not making any sense why they are closer. If let's say you have never seen cat and dog, they are kind of alien animals, right? And then you won't be able to judge that if they are similar or they are male or female or not. So it's like cat and dog, that's why you are saying yeah they can be similar, but computer doesn't know it. So that becomes very ambiguous, right? And this ambiguity we have to remove. Correct. And to remove this ambiguity, let's try to make kind of a table where we'll say there is animal, one table, right? And we try to get some properties of the animal. So let's say we'll take about tail, right? If animal has tail or not. We'll talk about fur, if they have fur or not. We'll talk about pet, if they are pet or not. We'll talk about wild, if they are wild or not. So let's say we take 4 different parameters, or let's say one more, we say how many legs they have. Legs. The last one is leg. So the animal is cat, then there is dog, right? And then there is tiger, correct? And then there is this lion, right? So this is how it's looking. Now if I say lion has a tail, yes. Fur, yes. Pet, no. Wild, yes. Lion has 4 legs, 4 legs. So you see, this is the way I can represent lion in terms of very basic properties representation in numbers. Like lion has a tail, lion has a fur, lion is not a pet, lion is wild, lion is kind of has 4 legs. Same goes to tiger. Tiger has a tail, tiger has fur, tiger is not pet, tiger is wild, tiger has 4 legs, right? And one more parameter, because see now you see this tiger and lion is becoming exactly similar, right? But we have to have a differentiation because we are trying to tell computer how to differentiate between them and how to find a similarity. Then let's say what is the major difference between tiger and lion? Let's say weight, weight, height. Like tiger is more like lion is very bigger and bulkier than tiger. So for weight I'll give it 10, and for weight I'll give it 5. So this is the different parameters and features that I'm deciding per animals. I'll go with dog. Dog has a tail, dog has fur, dog is pet, dog is wild, no, dog has 4 legs, yes. Is dog is smaller than tiger? Yes. How much smaller? So most probably like I can do 2.5, right? But still 2.5 is bigger, so we can do 2, right? And then if go to cat, cat has a tail, cat has a fur, cat is a pet, cat is not wild, cat has 4 legs, yes. What about the weight of the cat or size of the cat? You say weight could be in terms of size, you can take it. And this weight of the cat is kind of, let's say, uh, 1, for example. Now if I have to represent a cat, correct, then let's say this would be the representation of the cat. So I'll do it like 1 comma 1 1, like no, don't put comma, 1 1, and then 1, and then this 0, and then this 4, and then this 1. something like this is the representation of the cat, because now we have decided the properties and we have converted into numbers, right? Now, how you gonna represent a dog? The dog will be represented at this 1 1 1 0 4 2.5. How you gonna represent the tiger? The tiger represented like this 1 1 0 1 4 5. That is tiger. How you gonna represent the lion? The lion is this. Lion is 1 1 0 1 4 10. This is the line. Now you see, you try to find these are the very clues, kind of, let's say, computers are having more data to understand the difference between lion and tiger, and say yes, there is only one weight difference, otherwise tiger and lion are similar. There is only one difference about cat and dog, otherwise dog and cat are similar. So now what we did here, basically, we created, let's say, how many dimensions? I would say one property here, two here, three here, four here, five here, and six. So basically, we took around, if I do a list, so one property, two property, three properties, four properties, six properties, something like that, and this represented. So basically, there were six property, right? And that represented these numbers, and those numbers represented these animals, correct? Now if you see this property, you try to make this property bigger and bigger. You try to do it, let's say, I'll give you a number, then you'll try to understand it exactly. I'll say I'll give 1536 properties. This is exactly the embeddings that we do, right? That we try to do with OpenAI small model, or the text small model that we do embedding. If I say 3072, this is the embeddings that we do. If I think there is 4,000 something embeddings is also there to the bigger ones. So these embeddings are these values, you know, and that is the kind of embeddings that they create. These are called embeddings, and if I'll clean this up and we'll start a fresh new one. So now we understood there is a 1536 properties available, right? And these all properties are mentioned like this, and how many times is like 1536 times available, correct? If I'll go ahead 372, then the properties, or you could call it, let's say, I'll say a different color, dimension, then there will be 1 2 3 till 3072 dimensions available. All these dimensions will have their own property, yeah, right, own values, and these values will represent. So let's say if I'll go ahead with cat, if I'll go ahead with dog, if I'll go ahead with tiger again, if I'll go ahead with let's say lion again, and I'll not only settle myself to figure out only, let's say, six dimension. I'll ask myself to work more hard and hard to figure out everything about cat. Like, let's say, what is the nail size, for example, right? What does she eat? Correct? Is she pet or not? Means I'll try to figure out more granular properties, of 1536. Then it's become really closer and closer for these animals and these real world elements to be, represented in a number system, right? So now let's imagine there is animal 1, there is animal 2, there is animal 3, there is animal 4. So imagine there are only 4 words in the whole universe, that is cat, dog, tiger, and lion, right? And there are properties, 1536 properties of all of them, like 1 2 3 4 5 till 1536, correct? Right? 1536. And these dimensions, these dimensions, like if I'll cut it like this, for each dimension, like till 1536 or 3036, this becomes embedding matrix. Cool? This becomes an embedding or a color vector that represents the cat. Cool? Now imagine, keep on increasing this vocabulary from top and bottom. Let's say we have, let's say, 1,50,000 different type of words, and for all these words we have this kind of different set of dimension mechanism D1 to, let's say, D15 and 36, right? And that's what happens everywhere. That's exactly what happens everywhere. Let me make it bigger. Yeah, and I had to clean this up, right? So see, this is, and now you try to understand word to wake, correct? Correct. So word to wake that we did was kind of similar to it. There we're trying to figure out, king, queen, prince, and all these ones. But the whole point is now you say that, Abhishek, it is very easy for you to figure out cat, dog, and tiger, and lion, four animals, and only six properties like pet is not is she pet or not, correct? Is she wild or not, for example, and you did six properties, right? What about all these thousands and millions of words available in different set of kind of different languages? How they decide these properties? So they don't. No one decide these properties. No one decide these dimensions. No one decide this 1536 dimension. It is impossible to define for each and every language, for each and every type of content, for coding, or even 3072 dimensions. Who decides it? So no one decides. It's like each and every word gets a random number, correct? And it's like the random number. So the random numbers means the random matrix. So if I'll say 5936 dimension matrix, so D1, D2, D3 till D156, all of these will have, let's say, a set of numbers. So this is for cat, for example, or let's say you take it a different one. Let's say open is a word where it's gonna sit, or let's say king, where it's gonna sit. So they will be decide a random number, king 4 point, let's say 14 or 0.13, random number. This is the calculation part. This is where all the computes are going. So you do all these numbers, right? You set all these numbers, and then you try to read sentences. You try to read sentences that talk about, let's say, you said king, yeah. So you talk about king. Let's say lion is the king of the jungle, for example. Okay. Now this king and this lion has a relationship, and this jungle, correct? This relationship update these numbers. Looking at these sentences, like let's say cat is a pet, correct? But I did not say pet. Dog is a pet. A sentence that has been written by many years, and on the basis of these sentences, these numbers are decided in terms of back propagation. So every numbers get set again, and that's where this similarity happens. So that's where you try to figure out king, queen, prince, etc. Mango, apple, banana, fruit hai. It's a fruit, and that's what is now you. I think you got the whole point. You understood tokens as language atoms. You understood token ID as to represent those tokens in numbers. You understood the embeddings, right? And you understood the embedding matrix, right? Now let's try to understand the attention mechanism. Okay. So if you try to understand attention mechanism, just focus on this sentence that I'm writing. If I say that the cat was thirsty, okay, so it drank milk, right? We can easily tell that this it is representing cat, isn't it? So it is basically representing cat. We can tell from our understanding. So let's say my age is 32 to around 33 years. I have all these understanding of sentences. I am born and brought up in, let's say, Bhojpuri or Hindi language. but I understand, I comprehend English sentences, words. So now I can tell that it and cat belongs together, right? It is a representation of the cat, right? This understanding came once I read the complete sentence, isn't it? Right. I did not go from I understanding the and then did not go to understand cat and they did not go to understand was, did not go to understand. It's not, I'm just telling you, it's not like this is thirsty. It's not like I am just looking at single words. I'm trying to look at the combination of words that's making a sentence and then figuring out how each and every word is connected together. Correct? And then making sense of it. And then I'm trying to get that it belongs to cat. That is my understanding, right? So drank milk. So if I represent this, let's say this is the cat was thirsty, so it drank milk. Correct? How they do it? How LLMs do it? How transformers do it? Right? Transformer do. So there are mathematical formulas about query, what key you have, what values you can represent. All these Q, K, V values are there. We'll not go into that for mathematical formula deeper, but I'll help you understand how transformers understand. So what happens for every word, the transformer look at all of them together at once. It's not like the way we look at it. The cat was thirsty, so it drank milk, right? We did not process the and then went to cat. It's not like that. That our understanding of cat depends upon the, because we know cat is a cat, was and then thirsty. All this understanding of one word to another word to another word makes transformer learn it parallelly. You know, that's a major difference that they have done from RNN to transformer. Like looking at all words together, correct? And then what it does, once it had looked at all the words at once, then each and every word have their, let's say, metrics, representation in numbers, correct? Each and every word, each and every single word has these matrices, like we call them embedding, just we learned it, we call them vector, correct? While doing the dot product of these different words, they try to understand which word can come very closer, right? If I remove this and try to write again, the cat drank milk because it was thirsty, right? Then for each word, the we'll try to calculate the dot product of the and cat, and we'll try to get the value. And these dot products are basically, let's say, coming from the vector embedding matrix of these words, right? Then the cat, then let's say the drank, for example, right? And there are multiple permutation and combination that could happen to connect these different words, right? Correct? And these calculations happens all of them parallelly. And this transformer architecture understand all of them simultaneously and try to create values for each. So let's say for the and cat is try to generate, for example, 0.03% of similarity. For example, the and drank is try to generate 0.02% of similarity. Milk and it is try to generate, let's say, 0.10% of similarity. It and cat, let's say, is try to generate 63% of similarity, right? So these are the different similarities of different dot products of different combinations of words that we can get, correct? And these combination of words is kind of dot product of two different vectors or two different embeddings that we can calculate. And these embeddings calculate has D1, let's say, to D100, 1536 different numbers, right? So dog will have this, cat will have this, it will have this, right? All these different numbers. And once we try to apply the dot products, then we'll start getting the values. These values will be very random, right? It could be sometimes 93% similar, means 0.93, sometimes 0.73%, sometimes let's say 0.53%. To make it the complete probability as 1, we use softmax. Many people have seen softmax, yeah, top k parameters or temperature or the k parameter of while setting the LLMs. All these are coming from this softmax. Make sure if you have a sentence, for example, this, then whatever probability comes for this complete sentence should come under 1. That is the value. That is the thing that softmax does. And then once we have these complete values under 1, then we'll get the max closest or similar word, and we say this is how it could be connected, right? And that's exactly what it does, and that's how it does. So query word is, that is a q, is it, and look at all the words. So look at the, then animal, then street, then triad, and these are calculating the values. It says that it is an animal is 0.71 connected. So then we say that it and animal could have very close relationship. I have added these two papers over here also, so you can look at it. Attention is all you need, and the illustration about the complete working of this transform, right, and the attention mechanism. So the intuition is basically each token asks which other tokens are relevant to me, which other tokens are relevant to me. Then each token asks. So the cat drank milk because it was thirsty. It means each and every token, it's not like a single token, each and every token connects with other tokens, try to understand how they are related. And that's where it figures out the attention. And that's where LLM and transformer architecture try to understand whatever you write to them, right? And this is the query key value, the 3 learned projection that we send to them. If you open that paper, you will get a formula. There you will try to understand these 3 values will be passed. And these 3 values are coming from the sentence that you just sent to the LLM, right? And that's where decoder and encoder comes into picture. So once we send it, right, once the LLM try to understand the sentence, that comes into encoder. When LLMs try to generate the things, that comes into decoder. And this is the decoder concept that ChatGPT and most of the latent model works. So self attention is basically tokens attending within the same sequence. Yeah, and there is multiple heads that I just want to tell you what this multiple head is all about. So you see, multi-head, you say, it's basically try to understand the syntax, try to understand, let's say, semantics, try to understand the proposition, verb, noun of a sentence. This is a multi-head, and these all multi-heads happen parallelly. So once you try to put a sentence in LLMs, so it's not like first we do the syntax understanding, then we go to semantic understanding, then we go and understand the proposition or verb or noun or adjective. Everything happens parallelly. Like you get syntax, you get semantics, you get propositions or verb, adverb, adjective, noun, etc. Parallelly, all at once, simultaneously. That's where LLM has changed the world. That's where RNNs, right, has evolved. Let's say Google has made it evolve with the paper attention is everything and made this kind of transformer architecture, and with the help of encoder plus decoder, nowadays LLMs are able to build LLMs like Fable 5, where you do kind of cyber security vulnerabilities finding, you do Mythos, there is a Mythos class preview, correct? They are trying to figure out most cybersecurity vulnerabilities in the topmost software companies like Windows, Amazon, you can name it, Nvidia. So all these coming from a very basic understanding of tokens and their relationship, and then building these kind of models. And it's kind of evolution, of the understanding of these new transformer infrastructure, right? If you try to see this multi-head now, then you understand what this multi-head is doing. And it's all about trying to generate embeddings of each and every tokens, trying to make them in numbers, in embedding matrix that we learn. Let's say we try to say 1536 embeddings, we try to say 3072 embeddings, means these different dimensions of numbers that we can represent inside multi-dimensional space. And in that space, we can do all mathematical operations, like when we apply, let's say, dot products, we do multiplication of the inside the matrix, we try to generate another matrix from that matrix, that gives us this relationship between each other. Right? Now let's try to understand what is transformer architecture. Correct? So again, I have added this paper. Attention is all you need, and this annotated transformer where you can go and read about it. I just try to make it very straightforward and simple for you so that you can understand easily, right? Because we have lots of things to cover. We have all these things to cover in coming days, like prompt engineering we'll cover building with LLM APIs, embeddings, RAG, agents, tool. And if I say even RAG, right, it's not a simple RAG. It's like why RAG exists to the production RAG we'll go. We'll also discuss about graph RAG. We'll discuss about agentic RAG, corrective RAG, adaptive RAG. We'll talk about hallucinations about RAG. Means with this content and my personal expertise, so there are around 215 topics that we're gonna discuss in this complete video series if you keep on following up, right? So now let's try to understand the transformer architecture. So transformer is the network design behind all modern LLMs, stack layers of attention plus feed forward blocks that process all tokens in parallel. So this feed forward block is responsible for generating the next tokens and the next tokens till you get your answer that you could ask for the question, right? And the same thing you can get from this paper and this blog. It will explain about the complete structure of transformers, like how this feed network will work, right? Feed block will work, how this input embedding will work, like the test that you want to have about LLMs, that exact basic infrastructure. You can read this document and you can get it, right? For in terms of understanding AI agents and LLMs, I'm telling you what you need to know, so you don't have to do all the maths and all to crack an interview and get a job, or let's say understand AI agents, right? And this is the end-to-end flow. Like there is an input and embeddings happen, positioning also happen. So basically positions, embeddings I've already told you. Let's say dog bites men, right? And another sentence I read, right? Men bites dog. Correct. Both of sentences have kind of similar words like dog, and then men, and bites and bites. So it becomes really important to understand the position of these words, like how the position 1, 2, 3, 1, 2, 3 are set, so that the values can map properly. So even if we do embedding, so let's say we do 512 embeddings, right, of dog, correct? And then we generate all these numbers, like let's say D12, D1512. For all these numbers, when it comes in this sentence, then these embeddings will be different. And when we come to the second sentence, when man bites dog, then these dog embeddings will be different. So there will be another context will be added, so that the LLM can understand the different meaning of different sentences. Like there are different meaning happening here. Man is biting the dog, here dog is biting the man. So that's what happens in embeddings and positioning. And then self attention, when we try to understand each and every words, and feed forward will happen with multiple layers, and then logic gets applied, and then we generate the next token. And this is how the transformer architecture works, correct? Now if you try to understand these different keywords that I have written, right? Why transformer born? Because of the parallel. This is the major reason of the parallel processing. In RNN, right, recurrent neural networks, what used to happen if I write dog bites men, correct? Then you have to understand this word first, then this word, and then this word. So basically, one, two, three, if I write. So first, you have to understand dog, and then bite, and then man. If I don't have one, for example, then I won't have any idea about two, about bytes, right? And if I don't have two and three, then I won't have idea about three, like the men. So that was kind of a sequential framework that was happening in RNN, where we weights and biases we were trying to apply. But here everything happens parallelly. So dog bites men. If I do go to transformer, then all of these things happen with parallel architecture, like the embeddings, correct, the self attention mechanism, right, the positioning, all of these happen parallelly. Even the multi header that I told you, correct, all of these happens parallelly, and then LLM transformer understands the words, the sentence that we write to it, or even the para that we send to it, right? So attention captures long range dependencies, scales cleanly with more layers data. Attention is all you need is the original paper, that if you want to deep dive more, then you can read that, right? If you want, I can do another video just on attention is everything paper, all you need paper, right? And once you understand transformer, then it's become very easy to understand LLM. Though this is large language models, right? And when say Sam Altman says that Indians cannot build LLMs, you see the first person in 2017 paper is, I think, Ashish Vaishnaw, or something like that. I not remember the name correctly, but if you see, he is the Indian, and he was the first person, like out of seven, to contribute to that paper. So it's really bad if you say that it's all about the resources that we get, because of everything. So large language model is a neural network trained to predict the next token, that single objective. Even if you talk about like single objective, you said when I said earlier about multi-head, correct? This multi-head means that we try to understand the verb relationship with noun, the pronoun relationship with noun, the adjective relationship with adverb. All these things also we do, that we used to do with a time of word to wake, correct, and at a time of NLTK library that we used to work on, NLTK, Natural Language Toolkit, something like that. This was given by Stanford, correct. So this is all about the single objective at scale produces language, reasoning, and knowledge. That's the what LLM does. The core idea is trained on millions of token text plus code. So now you try to combine everything what I told you. I told you about byte pair encoding, right? Byte pair encoding. So there what we try to understand, we try to create words like if we have THE coming in. So we first see T, then we see H, then we see E, then we try to do TH, then we try to figure out THE, and we say that yeah, this could be a language atom, right? And this language atom becomes a token, right? We store it inside an array that becomes a token ID, correct? This token ID can be useful in terms of understanding and setting up these all different words, and that they have done. For each and every tokens that we have created, we do embeddings. In embeddings, we try to understand all list of different parameters that is available. Like we try to do D1, we try to do 2 till let's say D100, 1512 or 1536, or let's say 3072. For example, all the different dimensions for each and every single word. So let's say if we have 1,50,000 words, and for each and every word we have 1536 embeddings, then we generate a bigger matrix that has, let's say, 150k by 1536 dimension matrix, and this is we call embedding matrix, and each and every embeddings goes into the LLM as input, and once this input goes there, LLM does the dot product and does other matrix calculation and try to generate answer for us. try to correlate the different models. So everything is like related, and all these embeddings generated on the base of the text and word relationship after reading millions and millions of sentences and from dictionary or from books, right? And that's how everything has been built in LLM. So now hope you are getting my point. So trained on trillions of tokens, LLM, correct? So LLM is not a dictionary. You once you write into Chat GPT or Claude or let's say any LLM or Gemini or DeepSeek or even Llama Index or sorry Llama, then it's not a dictionary. That it's like a statistical, you could say, probability framework. I'll call it like it's like weights and all these different technology that I told you, decoder, encoder, right? All these creates a new tokens for you, right? So learns a probability distribution over the next token, generates by sampling one token, then repeating. Knowledge is statistical patterns compressed. So now if someone asks you what is an LLM, then you will be able to easily answer them. So now till now I have told you about tokens, token ID. I keep on repeating until you understand by heart, right? Tokens, we understood about tokens, we understood about token ID, right? We got to know about embeddings, correct? We got to know about embedding matrix, right? We got to know about vectors, we got to know about transformer, we got in the transformer we try to understand about how input embeddings goes, how positioning happens. Positioning means dog bites man, man bites dog. So these two words have same words. These two sentences have similar words, right? But they have a different meaning altogether. So all these we understood. We understood about, let's say, feed forward, correct? We understood about multi-head. We understood about softmax. We understood about P, K, everything, temperature. So that's what we understood. Now let's dive into the new one, that is a context window, right? Let's see what happens in the context window. So the maximum token a model can consider at once: system prompt plus hybrid history plus retrieved docs plus your question, it answer must all fit. Basically, once we try to build, let's say this is a LLM that we just built, and this has transformer, and the input that it takes, that is a maximum tokens. I already told you the difference between tokens and words. So you never compare, like you never take words as tokens. You have to apply thumb rule, like 4 character of word could be one token, correct? And then try to understand this sentence, that system prompt. So once we write system prompt, then we write these all different text, correct? And all these texts have tokens. So this token plus user prompt. User prompt is also a kind of instruction that we give to the LLM, because LLM needs to have an input, correct? And on the basis of these inputs, they try to apply all those backend technology that we talk about, like decoders and encoders, correct? Majorly, ChatGPT works on decoders; they don't work on encoders, right? So all these tokens of system prompt, user prompt, and retrieve document. It means, let's say we try to send some text extra than these instructions that we're trying to send, like user prompt or system prompt, right? We try to send the question that we have, and we want to ask to ChatGPT. All these consume tokens. So whenever we try to communicate with ChatGPT, it continuously keep on using tokens. So even we keep on, let's say, keep on asking question, right? So you see this chat of ChatGPT, you keep on asking question, it starts giving responses. Again, you keep on asking question, it starts giving responses, and this list goes on. Let's say suppose you communicated for, let's say, 1 to 30 days, right? For all these days, you're sending a message, you're getting a response. You're sending a message, so let's call it user message or let's call it model response. So there could be UM1 to let's say 1000, for example. So this is basically is user message. So keep on sending the message, and it's keep on sending the model response, right? And this user message model response also goes into that token, like system prompt, user prompt instruction, dog that I have received, the question that I have, and this context. That's the next thing that we're trying to learn. The context window, what is the context? So all these things goes in the LLM, and that's where it's try to connect all the dots together and try to answer you more personalized way, right? Then if we talk about again this, so there is a system prompt, there is a chat history and RAG, and there is a user message. So these all things that goes to the LLM and we get the output. That's how the current, let's say, all these different tools works. Like I call them applications. Like there is Claude, that is an application. So there is OpenAI that we use, that is an application. There is, let's say, Gemini that we use, that is an application. They work on top of these LLMs, right? So each one of them has their own LLM, and the most important part is once we try to communicate, we don't communicate with the direct LLM. There are safeguards on top of it. So basically, you can say something like this: once we send a message, it goes doesn't go directly to the core of the LLM. It goes on top of these safeguards that they have built. Correct. The policies that it has to go for. So you cannot ask wrongdoing things on ChatGPT or Gemini. That is stopped by the safeguards and policies that is built on top of these LLMs, right? And so that whenever we try to communicate, all these things go like system prompt. They have their inbuilt system prompt when we try to communicate with it. So it's like even ChatGPT chat message. They have their own system prompt, the very general terms of system prompt that they have built to help user get a better answer. Like you get a calculation, you get a coding snippet in the responses, you get, let's say, document get solved, you get a CSV get solved in the chat itself. So all these happens when they have given their own instruction behind it, right? And this all happens with this context window. Until unless you have the context window right, you won't get the proper personalized answer. That this is really important to understand. Correct. Now if you talk about this, the consequences, like exceeded, oldest tokens are dropped or truncated. This means once we are trying to generate user messages and model responses, correct, then what happens is the user is communicating for 1 to 30 days, or let's say 1 to 365 days or a year. Then these context becomes bigger and bigger, and this bigger context creates problem because there is a limit, and on that limit we can send input to the LLMs. So we have to make this smaller. That's what it's saying, dropped or truncated. We have to make this context more smaller. We have to write another, let's say, system prompt, so that the response, model response that it has given, we can make it smaller. We can make like smaller chunks, smaller sentences to explain all the bigger sentences that we have generated so far. Like we do, let's say, short-term memory. Like we'll understand in the coming videos. But the whole point is, it's like making them, smaller, and not letting their meaning get intact, right? Like meaning should be similar, but the representation of the text, because it has to convert to the embeddings, but that has to be become smaller. And there we try to apply different algorithms and techniques to make these chunks smaller. So like, for example, we'll talk about context pruning that we do, to make it smaller. We do caching also. We do short-term memory. We do long-term memory. We do, let's say, vector embeddings for all these messages that user do. So once you understand in the future, then the RAG that is built for the business, we can build a RAG for the simple user, a single user, right? So that there is a RAG, means knowledge base, and there is knowledge base for the user. That's what is trying to understand. Bigger window is not free, cost latency is rise, and this is the bigger problem that many enterprise businesses trying to solve, like token cost, usage problem, okay, latency problem. Because now the most important part is everything is based on our LLM, right? This is a reasoning model that we have, that we understood reasoning. Because once we try to enter the language items or tokens, and the context will be taken over here, then try to understand in the behind in the background, these LLM has to do all these calculation, right? The calculation is on based out of the tokens, not the length of the paragraph, but the how many tokens it will take, correct? And that's where they are trying to generate this kind of token usage cost, right? And this token usage cost we have to drill down in the enterprise companies, because there are millions of users coming in and using it. So that drop in truncated and this cost and latency is basically as soon as you try to send a message to the chat GPT, for example, to this LLM, it has to respond. Let's say you are in Mumbai or you are in Delhi, correct? And you are sending a message. Let's say this LLM is sitting and there is no caste or origin things, and it has to go to the origin that is sitting in US or let's say California. So this latency is there, right? And if every time you send new data, then this latency will remain same or sometimes will go bigger, but it will never go slower or smaller. Then we try to do apply caching, to make sure this latency gets solved. So loss in the middle models are trained best to start and end. This is why the RAG exists, and we'll talk about RAG in detail because we have the complete chapter over here, RAG. And in the RAG, we'll discuss about the retrieval augmented generation and what exactly it means and how things happens there. Correct. Now let's try to, and I think I have already told you why context matters in this context window one. So LLM has no memory between calls, right? The context window is its entire working knowledge for the request. Bad context is equal to bad answer. That exactly what I told you. If you try to see this, look at this paper, lost in the middle, right? So once we have the user message and we get the model response, this is the context that we have, like user trying to communicate, you try to ask a question. Let's say you try to upload a medical report, correct? Medical report is uploaded to chat GPT, for example. The transformer and the LLM will do all the things. It will try to build the tokens, it will try to build the token IDs, it will try to build the embeddings, right? It will try to build embedding matrix, right? It will try to understand the positions, it will try to do the multi-head. All these things it will do, and that's what tokens they'll count, and for those tokens they will cost you, correct? And after once you send it to them, and then you keep on asking questions. You keep on asking questions about, let's say you ask about what kind of medicine doctor has prescribed. You try to ask what kind of report that user has to do, for what have to kind of test that they have to go through. So and then this is the model only knows what's in the current context and its weights. Relevant well-ordered context beats more context. And the noise junk in the context actively degrades answer. Engineering AI is going to engineer what goes into the window. So this is what we have to make sure when we try to build agents, and in terms of, like, let's say when we try to define the system prompt, that will go to this, what do you call, LLM. We try to understand the user prompt, correct? That goes to the LLM, because once you send these user prompt, system prompt, and let's say even skills, correct, that we do generate with, let's say, Claude MD, right, or a skills.md file, learning.md file that we generate with Claude, or let's say Codex. All these, when they actually goes inside these LLMs, right, then the same things happen, like it has to come to token, then token ID, and then embedding metrics, and then vectors, and then position will happen, and then multi-head will happen, and they'll try to understand. So more bigger system prompt will try to create more token cost. More bigger user prompt will try to create more token cost, because it has to process the tokens, like 4 characters, single word, single token, language atom. All these things you have to remember. More better context, like let's say if you talk about knowledge base, where we try to store the vectors that or embeddings that we generate. That is, let's say, knowledge base that we call, let's say, it's a vector database, right? And these vector database has to populate with the proper, actual, non-violent or unrelated documents. It has to be related documents embeddings stored, correct? So all these things has to be make sure while trying to build the pipeline, or let's say the agents. Let's say try to understand the inference pipeline here. the runtime path from your request to response, like so this is, I keep on explaining you all these stuff. You see, tokenize and then embed and then the forward pass and the sample token and the repeat until done. That is auto regressive generation. That's what happens in inference pipeline. And this one inference pipeline is basically, this is a LLM and there is a safeguard. This is a safeguard, right? And there is, let's say, a policy that has been added. This is a core brain over here. And then once, as soon as an input comes in, right, all these things happen with that input, like the tokenization happen, like understanding the tokens and the token ID, and then the embeddings happen. So let's say that you select 1536 or 3072, or let's say even 512. All these embeddings will happen and the embeddings will go, then positioning will happen, then feed forward network will come, then multi-head will happen, and then it will try to understand and try to respond back to the user. That is one complete inference. Yeah, and if you talk, if you want to see more about it, so you can go over here and you see transformer inference arithmetic. From here I try to understood how the mathematics works, but that is not important for this course, so I'm not taking it in, right? And these are the different stages. So you can see prefill, decode, KV case you have seen multiple times. Samplings, keep on seeing it, because whenever we try to send, we try to send top P and top K, all these value like temperature, all these value will send, right? That is like common. KV cache is there when you don't have to recompute it, correct? Decode is there, like decoder, coder, encoder, correct? And there is decoder, isn't it? So decoder is responsible, like generate one token at a time and sequentially, right? And prefill is a process the whole prompt at once in parallel. That's all these stages that happens in the inference pipeline, correct? Now you try to see over here, try to see how the next token chosen. There is logits, softmax that I have told you, then temperature, then top K, top P, and then that will pick the next token. Because see, softmax is really responsible. Softmax is kind of, if I do softmax of these cat is a pet, right? So then how cat and pet is correlated, so and how cat is correlated, how cat A is correlated, how a pet is related, will generate different set of similarity score in percentage. And once we do softmax, then we try to do that for all these different words, there could be max. If we try to add all the similarity, then it will come, let's say 1, for example. That's why we do the softmax. Then that's how the inference pipeline work. Then we'll see the reasoning model. Inside the reasoning model, you'll see there is produce a chain of thought, right, before the final answer, correct? So model trained to think step by step before answering. That is chain of thought. They try to understand what user has sent, what I have to do, what to answer it. Break the bigger problem to smaller problems and try to generate the answer. That is chain of thought that modelers behind the scene. There are, if you look at this paper and this paper, then it will tell you exactly what chain of thoughts, how actually they divide these into different segments, and they generate hidden reasoning tokens, trading extra compute for higher accuracy on hard problems. That's all about the tokens and the chain of thought. Much stronger on math, logic. Like let's say that even if I have to do 2 plus 2, that equals to 4. So what chain of thought I applied? So if I do 2 plus 2 equal to 4, or let's say I do 2 plus 2 to the power 3, right? Then what process I'll try to apply? I'll try to first add 2 plus 2, that will become 4. Then there will be 4 to the power 3. Then I'll do 4 into 4 into 4, and then I'll calculate, let's say 4 4 is 16 into 4, and then I'll do 64. So all these steps I have taken, that is chain of thought, and that's what is trying to explain to calculate the final answer. And there is a cost and latency scale with thinking length. That is there. We'll see about thinking in coming videos. Because thinking is there that allow models to think about the content that you give to them. Correct. Model of experts models. If you try to see over here, then this is basically, it splits the network into many experts or sub networks. That this pattern we'll see in terms of when try to build AI agents, right? When we try to build AI agents, then we'll try to see these patterns. So the tokens will come, their router will be there, then there will be expert 2, 3, 4, and then they try to combine and give. the answer, like dynamic programming, when try to break the bigger problem into smaller chunks of problems and keep on solving that small chunk of problems with the expert of its kind, right? So that is the mixture of expert, if someone will ask you, and huge capacity but only parts fire per token. So what's its used for? What's is used is more parameters, knowledge without proportional compute. A router picks top k expert per token, cheaper inference than a dense model of equal size, powers many frontier models like Mistral. So Mistral is an open source model. DeepSeek is also kind of, you can use this model at your own server. You cannot use. So this is a bigger difference that I want to highlight. So like let's say there is DeepSeek, correct? So you can take DeepSeek and you can host it on our EC2 machine, right? And then on once you host it on EC2 machine, let's say you try to use GPU, because of all these matrix calculations, correct? To do the tokens, the token ID, the embeddings in embedding matrix, to build that vocabulary, and to, let's say, understand the position of the words. Once it fires you these LLMs, then you need that high power computation, correct? And that's why you need GPUs, graphical processing units. And these models you can host it on your own GPUs, but that doesn't happen with OpenAI. You cannot host OpenAI on your own server. You have to use their API call. So they are like closely sitting on their own server. You can just hit them with the REST API call, or let's say a socket or a streaming API call that they offer, like the SDK software development kit that they offer. You can do only that. Even the similar case with Anthropic, you cannot host their model. Even let's say you use Bedrock, correct? Bedrock has these models. So with Bedrock, AWS, basically AWS Bedrock, you can use these models, but you cannot host it on your own server. What is the difference? If you ask Abhishek, what is the difference between hosting these models on our platform, on our servers, on our let's say machines, and using them directly? So once you try to host it, you will pay GPU cost continuously, right? The compute that it will run, like let's say it will be kind of hourly charges, let's say $100 per hour, for example, to host it, correct? But when try to use these Anthropic and these LLM models, you have to just pay for the token usage, right? It's like it's for the entire world, and you want to be very, very specific and very closed in your own environment, that we have to go through this route, and you can be sure, because they do not send data from once they are hosted on a server to their own server, until unless you, let's say, you activate the kind of analytics platform data, etc., so that they won't go. So this is what all happens with DeepSeek and OpenAI and Anthropic, right? And that I think this is the beauty of it. And the bigger the models are, the better they are trying to train and putting in the closed loop, but still they're trying to expose it to general public so that they can use and build greater products, right? If you look at the evolution of GPT, so GPT is so this is generative pre-trained transformer. This is generative. Okay, now you totally understand this works on mechanism of decoder. Decoder is trying to build the next tokens, correct? And these next tokens help you answer all the questions that you ask. And this is how the evolution happens. And this GPT basically creates OpenAI, right? Or let's say you call it Chat GPT, and that we keep on using it. Similar way, Anthropic is there, that we try to use it, correct? So there is GPT-2, there's coherent long text but no instruction following, that was there in GPT-2. Few sorts learning were there. So two examples it generalizes. There was RLHF, human feedback, reinforcement learning, human feedback plus chat. There was a Chat GPT movement when GPT 3.5 came, right? I think this was the major video that we saw about sending, let's say, a text, and it was generating an complete HTML page by itself, or let's say a website or landing page, right? There is GPT-4, that is multimodal, far more reliable reasoning, And then we have the GPT-5 era. When we are talking about Soul, Terra, Luna, right? When we are talking about, this is GPT 5.6 family, right? When we are talking about Fable 5, correct? When we are talking about Mythos, class, preview, all these models are like frontier models. They cost really great, many much more times, but the work that they can perform is really great at the very high level. Like, it's better than a senior solution architect, or better than senior software engineer, or senior AI agent developers, or let's say even the CTO. So this is how the current things are moving, and this is how these are like kind of trained and built from scratch, and that's really amazing. So these are the 5 different things that you need to like remember. This doesn't ask, but you have to remember what happens. There is a word, this fine tuning versus prompting versus RAG. So 3 ways to make your model do a task. So basically you have a task, correct, and that task you need to solve, and to solve this task you have to put into the LLMs. And once this goes to the LLM, there is an output that comes out. So this is the input and this is the output that comes out. So you see 3 ways to make a model do a task: change the prompt, retrieve external facts, or update the weights. Pick by need. Most problems don't need fine tuning. Fine tuning, I'll explain. This is the RAG paper that you should read if you're trying to go more dive, right? So the approach is, first is prompting. Like, before behavior format change, that's what we do over here, that I was telling you about the input. We send it with system prompt, user prompts, or even skills. All these are tokens, language atoms, correct, and let's say you can call it instructions for the GPT. There is a RAG. RAG is basically, so these, once we understood what is LLM, that was trained on these transformer with trillions of words and sentences. Then if you see LLMs and then trained on, let's say, 30th of July 2026, but let's say today is, for example, 11th or 12th of August 2026. So the information that flowed from 30th July to 11th, I guess, this LLM won't have. Or if a private business is there that has never made some documents to internet, then these LLM won't have. That's where RAG comes in. You have to like create your data, your business data into that part, like the tokens, and then the token IDs, and then the embeddings, correct, and then embedding matrix, and store it in the vector database. That's what we actually do when we use text small embedding model to generate these embeddings, right? And that's where it gets stored, and these LLM connects with that knowledge base, or you could say vector database, or embedding matrix database, or you could say RAG. And whenever the need is, they try to connect with it and get the answer. There is fine tuning. Need a consistent style of or narrow skill at a scale. So basically, I'll give you a better example. So there is a Paytm in India. So this is Paytm. For example, they are in FSI business. For example, finance sector, I think insurance, finance, loan, etc., banking services, FSI sector. Now, once we make the payment, then it says that 200 paid to the business or to the vendor. Now this, let's say they give us ad over here, correct. Let's say they want to keep on generating the ad, different type of ad on the base of the user preferences, on how user behaves on the mobile application. Then let's say they try to use LLM, and let's say they use DeepSeek, for example, or they use Meta Llama, correct, 3.2 or something like that, or latest version of it. Once these ad has to be shown, then it will go to Llama, and the Llama will tell, for this user profile, show this ad, correct. So this Llama can be trained on the base of the FSI business of Paytm, and then we do prompt tuning, fine tuning, and we try to update the weights and parameters of these Llama, so that the sequential or the multi-head things happens, that will happen on the base of these FSI business model rather than the actual general model that they have. So the benefits of it is it becomes really faster, it doesn't hallucinate, right? And it becomes part of your own business. It becomes your own business, right? It doesn't do all other things. Correct. And then there is a model comparison that you can see over here, right? Here is like Claude, ChatGPT, Gemini, Quinn, Llama, differ in reasoning, context size, multimodality, cost, open versus closed. All these different models are there. So if you try to build an agent, right? So there is, we have to make sure we understand the model, we understand their cost, we understand what they are used for, correct? Their reasoning capability, if they are available for a tool call or not. So all these things we have to first understand, like how much cost they do it for, let's say 10 million tokens, the tokens that we push in, and how much for the output tokens, because there is encoder and decoder, both will take the input and produce the output. Both time they have to do all the calculation of matrices, and they, on the base of the token, they calculate these values, correct? And that for input to the LLM and to the output, we have to pay cost both the places, correct? And for each and every company, like let's say Claude or GPT, Gemini, Quinn, Llama, they have all these different, kind of uh, characters of these LLMs, right? There are also benchmarking, multiple benchmarking. Was there, let's say, for example, there is a terminal benchmark. So I'll explain you one, and then you will keep on understanding other benchmarks. So benchmark basically is making like kind of a leaderboard where you rank these models on certain tasks. So if you talk about terminal bench, right? So you already understand terminal, right? Terminal is basically trying to solve. Let's say you do cat, you do cd, you try to create an nginx script, right? You do git clone. All these terminal tasks that you do, if all these models like Claude, GPT, Gemini, they have, let's say, given, let's say 10,000 tasks on these list of things, and once they perform these tasks, then they try to note it down, like what is noting, let's say how much token they'll use, how much time they'll use, how much cost they'll use, and on the base of this they'll try to give it rank 1, 2, 3, 4, blah blah blah, and that is the terminal benchmarking. So now today we have covered the complete LLM foundation. The next time we'll try to complete the prompt engineering this way. Okay, so hope you like my videos. Make sure comment, ask me questions, join WhatsApp community so that I can share this valuable study material to you. Yeah, thank you so much.